Hello, my name is Tommy, and this is a recording of a talk that I gave at an IT conference. The title of the talk is The Average Value, and the intended audience are intermediate level data scientists. In this recording, I will just go through the presentation very informally and talk a little bit around it. I'm not limited by time here. I'll assume that you are someone with a little bit of mathematical background and that you're interested in data science, essentially. If you want to look at these slides as I go through them or afterwards, or look at the references, you can download them from this URL. So the average value. This is the equation for it, and if that was all there was to say, it would end here. This slide does introduce some notation though, but obviously if we're gonna make a presentation out of this, we need some way to generalize away from this equation. We'll do that by looking at the optimization problem that this equation, the arithmetic average, solves. And that's the least squares optimization problem. In general, in machine learning, when we do regression tasks, it's very common that we have squared loss and we have some kind of function f, and we want to compute the optimal parameters for f. Here f could be a tree-based model, could be a linear regression, neural network, and somehow we find the best parameters theta. How we find them, however, is not, there's no closed form equation typically. So for the arithmetic average, there is a closed form equation, but for many more complicated models, you use something like gradient descent or Newton's method and you end up with a result. But there's no equation that you can use to just compute the results. It's always some iterative procedure, and in many problems there's no guarantee that you have a global minima and that you always end up with the same one. So basically this talk is not really about the average value. It's about setting this model f to be a single parameter model. So we set f of x theta equal to theta, and we just ask ourselves, what else can we do then? If we fix the model to be the simplest possible model that we can think of, what else can we do? Well, we can tweak the loss function. So instead of looking at squared errors, we can do other things. And in this presentation, now finally we get to the table of contents. In this presentation, we'll first look at the Pythagorean averages. It's the arithmetic average, the geometric average, and the harmonic average. And we'll see that there are some loss functions that induce these averages in a very natural way. We'll then look at the p-norm, which you might know about. It's a way to measure distance, and we can use that to get the notion of the median and the midpoint. We'll look at Huber, mellowmax, and quantiles, which are, what should we say? They are one parameter models for sure that go a little bit further away from the Pythagorean averages and the p-norm, and they're maybe perhaps a bit more rarely used, but still very useful to know about. And then at the end, we will look at some examples from the real world. These are aimed at developers. One of them is ETA for file downloads. How long will it take to download some files? The second one is ranking products by ratings on websites. So let's jump into it and look at the Pythagorean averages. So the arithmetic average, that's the common one, and it minimizes squared loss. We've seen this before. There's an assumption here that if you're twice as far off, it's 4 times worse because you're squaring things. It has really, really nice mathematical properties. Basically, if you have squared loss, you have a quadratic, so if you differentiate it, you get something linear, and you can solve that. So you can solve that immediately. So basically, Newton's method can solve this in one iteration. You can one-shot these squared problems using Newton's method, and that's a very nice property to have, and it's very nice mathematically. This figure is important to understand. It shows for each data point 1, 3, and 6 the loss, and then it shows the sum of these three losses over the three data points, and that's the solid blue line. And this is the loss function. If you minimize it, you get the arithmetic average, and that's what's shown here in this dashed line. So I'll make one final comment that's in the footnote here, and that's that how do you get this in the first place, the squared loss? Well, one way is to look at the normal distribution, which is essentially an exponential to the power of squares. But you also end up with averages in Poisson models and binomial models and other types of models. So there are many types of assumptions about data that can introduce this kind of problem. The geometric average, it minimizes multiplicative loss. So if you take the logarithm of the data and the logarithm of the model and you compare those, you get the multiplicative loss. And here, being one order of magnitude below is equally bad as being one order of magnitude above. That's what it means. As for the geometric average, it's like the arithmetic average, but with multiplication. So the arithmetic average has the property that it's the number that you have to add to itself n times to get the sum of the data. The geometric average is the number that you have to multiply with itself n times to get the product of the data. The harmonic average minimizes relative loss. So here you measure loss compared or errors relative to the true value. And this is equivalent to doing weighted least squares, where the weights are given by 1 over y. This particular loss, the relative loss, is not the only loss function that induces this notion of average. This loss in the footnotes will also lead to the same harmonic average. But this is one that's, I think, more natural and more commonly used. It's called the mean average percentage error often. Okay, let's look at these three loss functions in a different problem setting. So just going away from the averages a little bit and looking at loss functions. Suppose you have some resources that you want to distribute. Maybe you have bakeries and you have a prediction for how much bread you're going to sell tomorrow. You have a central bakery where you bake a lot of bread and you want to distribute so that you cover every store. Unfortunately, you don't have enough bread to cover every store, so you need to distribute according to some rule. You would like your distribution theta to be as close as possible to the demand of each store y, so you use a loss function. Depending on which loss function you use, you get three different distributions. So I think that's a nice way to examine these loss functions in a different context. And here I'm not sure what the correct answer would be. It would probably depend on what the goal of the bakeries is. Would you use the squared loss in the real world, multiplicative loss or relative loss? I'll leave that up to you and let you think about it. Okay, so we have seen a few loss functions now. We're going to see even more, and it might be interesting to discuss a little bit how you would choose a loss function. So every loss function has the property that if your prediction is very close to the target, it's good, and if it's far off, it's bad. And then you want to minimize the error. So how do you choose between loss functions? One thing that I like to do is to consider the null space. And what I mean by that is just I consider which types of errors are equally bad, and does that make sense in the application that I'm looking at. So for instance, if the true values are 2, 8, and this is like not the average now, it's we predict on each of these. So 2, 8 is the true answer. And squared errors would imply that if I go 2 up in the positive direction on the first prediction, or 2 up on the second one, that's equally bad. What about multiplicative errors? It means that if I predict 8 over 2, so 4, or 8 times 2, then that's equally bad. Relative errors means that if I subtract 2 here, I go down with 2, or I go up with 8 in the second one, that's equally bad, because that's what the true values are. I go up one unit of true values, and I go up 1 unit of true values, and that's equally bad. So here are some practical examples. Say you're trying to predict how much medicine to dose, or how much drugs to give. You probably want to use relative errors. So if you have different drugs and they work on different dosages, you probably want to do relative errors, or you want to do something like multiplicative errors. If you're predicting economic outcomes, you're trying to predict investments, then you probably don't want to use multiplicative or relative errors, because there's nothing relative about money. 1 unit of money, whether that comes from project A, which is a small project, or project B, which is a huge project, it's still 1 unit of money. So you don't care where it comes from, or it's relatively good or bad, you just want to maximize money. So then you probably want to use squared errors, or even more likely, you want to use absolute errors. Because the assumption that if you're twice as far off, it's 4 times worse, that doesn't really hold with money. Being twice as far off means losing twice as much, which is twice as bad, not 4 times as bad. Unless you want to get into the utility of money and things like that. But let's skip that for now. When people look at interest rates and they compute the average interest rate, they always use multiplicative errors, or in other words, they use the geometric average. The same when people summarize performance benchmarks, computers, CPUs, and things like that, they use the geometric average. Having finished the first part about the Pythagorean averages, we're now going to talk about the p-norm. We're going to generalize this equation in a different direction. We're going to solve this optimization problem for different values of p, instead of p equals 2, which is the arithmetic average. If we set p equal to 1, we get the absolute error. This is an absolute value function placed on each data point, and when you sum it up, it's piecewise linear. If there's an odd number of data points, there's a unique maximum. If there's an even number of data points, it's flat between the 2 data points in the middle. There's no unique minimum. The median also has a property which is a little bit interesting. It's that if I were to change this data point 6 and move it up to 8 or down to 4, as long as it doesn't cross 3, the median is the same. So the median as a function is completely ignores the location of every data point except for the one in the middle. Obviously, if 6 crosses 3, then something happens with the function, but it's blind to a lot of the data points if you jitter them around, essentially. P equals 1.5 is one of many ways to create something that's between a median and an average. It's also the first optimization problem we have seen where there is no easily computed closed form solution. Here you would use some optimization routine, iterative routine, to get the minimum. P equals 2 is the squared error, which we have seen before. As you increase p further, the functions become more and more sharp, and you get to an interesting property in the limit as p becomes very large. When p is very large, minimizing the p-norm is equivalent to minimizing the maximum. And if you want to minimize the maximum distance, then you want to make the worst case as good as possible, and how you do that is to place yourself in the midpoint. So this is the high school, it's one of the measures of centrality that you might have learned in high school, is the midpoint. So here it would be 6 plus 1, 7 divided by 2, 3.5, and this is what it looks like as a function. So how can we combine these Pythagorean losses and p-norms? First, let's put them up in a table. Some of them are well known: mean absolute error, mean squared error, maximum error, not used that much in machine learning, but used in engineering, where you want to make the worst case as good as possible. If you are, sometimes like if you're creating a plane or something, plane, elevator, you want the worst scenario to be as good as possible. So you want to focus in on that, not the average case. Here we see the mean squared logarithmic error, the mean absolute percentage error, and the weighted mean squared error. There are some that are not here, but you can imagine them being used. For instance, here with p equals 1 and the multiplicative error, this would be not a mean squared, it would be the mean, be like the median logarithmic error. I think so, I think I would call it that. Or maybe mean absolute logarithmic error. Yeah, I think that's a better name for what we could call this. But the point is you can construct and combine these functions together. How would you do that? You can first look at an individual data point and consider what kind of loss function you're interested in, and then you can use a p-norm to combine them. So the p-norm is a way to combine the individual losses. You can think of it that way. You can think of what properties do you want in your application. So if you're choosing a p-norm here, the absolute error means that 4, 0 is as bad as residuals as 3, 1 and 2, 2. So again, with money, this is a good example. If you're 4 off in your investment, you probably don't care that much if it's this one or this one. If it's money lost, you lose 4 anyway. So there's no point in trying to balance your errors if you just want to make as much money as possible or lose as little as possible. It also means that 9, 0 is better than 5, 5, even though errors are more balanced in 5, 5. It sums to 10, which is more than 9 plus 0. Maximum error, of course, just looks at the largest value. So 9, 0 will then be as bad as 9, 5 and 9, 9. While 8, 8 would be better than 9, 0. So the sum here does not matter, it's just the largest value that matters. Now we're going to look at even more esoteric notions of averages, notions of maximum and minimum, and everything in between, really. One issue with squared errors is that they can be overly sensitive to outliers. And one remedy for this is to use the smooth Huber, which acts like, if you zoom in, if you're close to 0, it acts like a square, but if you zoom out, it acts like the absolute value. So then it will not be sensitive to outliers, because far away from 0, it will act like the absolute value. But it still has a unique minimum if you have an even number of data points, for instance. There's an opposite problem that might happen in some applications, and that's that squared errors are very flat around 0. So if you have a small residual and you square it, it will become even smaller. So if you're regularizing coefficients, for instance, like the lasso does, and you want to drive them all the way to 0, it's very nice to have something that acts like the absolute value close to 0 because it drives the coefficients all the way down. So the reverse Huber has the opposite effect. It's like the absolute value when you're close to 0, and it acts like a square if you're far away from 0. Mellowmax and mellowmin, these are relaxations of maximum and minimum. So they are functions that in the limit here, as alpha goes to infinity, this thing approaches the maximum. As alpha goes to negative infinity, it approaches the minimum. And if alpha is around 0, it will go to the arithmetic average. So if you want something that acts like something in between the arithmetic average and the maximum, mellowmax is a nice way to do it. The maximum also has the property that, of course, it only depends on the maximum value in the data set. But sometimes if you want to minimize the maximum, for instance, you want to bring values down, and then one way to do that is to drive down the maximum value. But as a function, the maximum is blind to every other value apart from the largest one. So if you use mellowmax instead, it's actually a little bit sensitive to other values, so it can inform the optimization routine that you're using. So sometimes it's very nice to be able to relax these functions that are really, I imagine them being like piecewise linear somehow, or their derivatives as a function of many data points are 0. Like the maximum only depends on one value, the median only depends on 1 or 2 for most inputs and most small changes. And if you want something that's a bit more smooth, then this is a nice option. I'll show you what it looks like, the function that it minimizes on the left here, and on the right the value for theta, the mellowmax itself. So as I increase alpha, notice what happens to the figure. As alpha increases, it goes more and more towards the maximum at 6 here. This slide will be very quick. I assume you know about quantiles. It's a way to be somewhere in between the median and the minimum and the maximum. It puts an absolute value function on every data point, but it will scale it up and down on the left and right. I'll mention a little generalization. There's no reason that we have to use the absolute value. We can use squared residuals 2, and then if p equals 2 here, you would call it an expectile. But in general, there's no reason you don't have to go for p equals 1 or p equals 2, even though there are some properties that you get when you make that choice. You could in principle use any value for p here. Let's look at the first practical example, ETA for file downloads. So suppose you're a developer and you're writing some routine that will download files or copy files or install some software. So basically the computer is doing some work, and it's doing chunks of work, and you have the time that each chunk takes, like files downloaded, and you know the amount of work done. You also know how much work will be done in total. For instance, the total number of megabytes for all the files you're going to download, and you want to estimate how long will this take. So to solve this, we need to be able to handle non-equidistant arrivals. This could be non-equidistant times or non-equidistant pieces of work. We will assume that a linear model is reasonable. That doesn't mean that the parameters of the linear model can't change. If I start downloading files and you get on the network, you start downloading stuff, then of course my download speed will go down. But after it goes down, we can assume that it's linear still, just with a different rate. And also very importantly, when a new data point arrives, we have to be able to update our model in constant time. So we we don't want to keep track of all these data points. We don't want to iterate over all the data points or see any previous data points when a new data point arrives. We have to be able to update the model instantaneously, because there could be millions of data points in these types of models. So here's one idea. We can compute the average rate of work. So if we have two pieces of work, two files that have been downloaded, we can compute the slope for each of these pieces of work. So work done over time elapsed. And then by minimizing this function, we get this theta, which is the average amount of work done per time. I weigh this by delta time here because when I solve that optimization problem, it leads to this equation, which has a nice symmetry, dy over dt. It also should make some intuitive sense that if I download a file in 1 second, then that contains some information. But if I download the next file in, I don't know, half a minute, that's a lot more information. So delta time is larger, and then that should be weighted up even more. This wi we will use to weight the most recent data more heavily. So we can split it up like this. The most recent data point is attached at the end. So we have the previous estimate, we get some new data, and we can very quickly just update by keeping track of our previous computation and adding this to it. We then take a linear model, we constrain it to go through the last data point that's seen, that's the last blue one in these figures. We have 1 degree of freedom left, and we use that degree of freedom on the slope and use this estimate for the slope. We set the weights equal to or proportional to some number to the power of I over gamma, where gamma is the half-life, and this is just a way to parameterize these weights. And the effect is that the most recent data is weighted more heavily. Here you see how it performs. If the speed changes when we see more data in the future, then obviously it's not a very good model. If it's linear all the way through, then it's quite accurate. Here there's some deviation from linearity. Here it's a bit more noisy. You see it goes through the last data point. Picks up an average rate that's somewhere in between, and it's quite close. As more data arrives, it will actually improve here because it'll pick up on this new regime where we have a higher rate of change. Here are some figures showing what it looks like with one slope, 2, 3, 4, 5, and that's the last one. So it's a simple algorithm, very fast, very accurate in many real-world cases. Depends, of course, a bit on the application, but very simple application of using one-parameter models to accomplish some cool stuff that's probably more advanced than some of the file ETA estimates are and other ETA estimates. At least from what I've seen, they are a bit jittery and jump about a little bit too much. Okay, final example is ranking products by ratings. I think this is a very interesting example from the real world of how you can use averages to do some pretty cool stuff. So I went and looked at Norwegian e-commerce websites and other websites that rank stuff. So on all of these websites, users can give a rating, and these ratings can be used to rank products. But all these websites use a naive average rating, and that produces some pretty strange results. For instance, the average of 5 is 5, but the average of all these numbers is slightly less than 5. So it will say that this product is rated more highly than this product, which has all these ratings. But I would trust this product to be better because it has so many more ratings. This one has just one rating, and that doesn't make me very certain that the true quality of this product is very high. But here you could have 100 fives or 1,000 fives and just one 4, and it would make this product be ranked lower than this one. And I think that's wrong. What a lot of these websites also do is that they place the products that have no ratings at the very bottom. So a product that has ratings 1, 1, 1 all the way through will be ranked before the products that have no ratings. And I think that's wrong. If you have a new product that doesn't have any rating, what that means is that the product is likely average. It doesn't mean that it's the worst product and deserves to be ranked last. I didn't find any e-commerce website in Norway. I didn't look at international ones, but I don't think I found anyone there who does this correctly. One of the few that gets this right is the IMDb top 250 list. They do account for the number of ratings, and they use an equation that's, I think, very similar to the one that we're going to deduce here. We want our average rating to have two properties. It should take into account the number of ratings, and a product without any ratings is likely typical, not really bad. It doesn't deserve to be ranked last. So here comes a very important idea. What are we really doing when we're trying to rank products? We're going to frame this as a prediction problem. We're going to say that what we're really doing is that we're predicting the next rating. So if you were to buy this product and you were to rate it, what would your rating be? That would be the next rating for this product. So we're going to cast it as a prediction problem and say that ranking products is equivalent to predicting the next rating and then sorting by that prediction. And the way we'll do it is that we will introduce a prior average y bar and a pseudo count alpha. We will solve this optimization problem, and the solution is this. So here you see the meaning of the pseudo count. It's added to n as dummy ratings, and the value of the dummy ratings is y bar. So that's the prior average rating. To determine the hyperparameters y bar and alpha, we need to do some cross-validation. I assume that you know about leave one out cross-validation and k-fold cross-validation. We are going to do leave next out cross-validation. So it's very important with cross-validation that you define your cross-validation procedure to be as similar as possible to how you want to use the model. And we just defined that our notion of ranking, it means predicting the next value. So we're going to simulate that exactly. We're going to do something like this. Start with no ratings at all. Try to predict the first one. Then we get to know what the first one was, and we look at the residual, squared residual. Then we have access to that first data point, try to predict the second one. We get to know the second data point, compare, and then we keep going like that. This is a time series split, essentially, where you just get to learn one more data point at a time. Both of these can, in these simple models, they can be computed in linear time. So that's nice. So computing the average is as fast as computing the leave next out and leave one out cross-validation numbers. So it means we can do this very quickly. Let's apply it to a data set. There is a Norwegian website called Legelisten that ranks doctors. So I went and found 17 doctors that have in total 212 ratings. I use our average here, but I also added some weights, and I parameterize those weights by the half-life gamma. Then I use leave next out cross-validation to get the best values for hyperparameters alpha, gamma, the half-life, and y bar, the prior average. So the optimal number of pseudo ratings is around 2. The optimal half-life is around 7 years for these doctors, and the prior rating is 3.8, and these doctors are rated on a scale from 1 to 5. The loss, if we just use the arithmetic average as our predictor of the next rating, was 1.77. With this regularized temporal average, it's 1.55. And that's a very nice reduction in loss and leads to better predictions of the next rating. So the rating that you would presumably give when you go to this doctor. You could say that why not make this into a big, full machine learning project and use all kinds of covariates. But I don't think people would like that. If you rank these doctors and you used information about their gender and their age and things like that, it's probably not good. But this is probably something that people will understand, and they won't feel like it discriminates perhaps unfairly on age and gender and things like that. So I think this is a very simple model, still super simple, but just a bit more nuanced, and it's created from thinking through the problem a bit more carefully than just using the average. Here is the rating that was used on the website last I checked, which is a little while ago now, so they might have changed it. That's in blue. And here is my proposed rating in green. I want to look at 3 of these. First is the third doctor. One person has rated this doctor with a 5. The old ranking puts him or her first. We say, no, 1 rating is not that much. We're going to pull you a bit down. So actually, this doctor that has many 5s is probably better or deserves to be ranked higher. The 10th doctor is this person. Very interesting because he or she is pulled away from the grand average. Typically, if you don't have or always when you don't have the temporal weighting, you will pull towards the grand average. But here it's pulling away. This doctor has gotten more positive reviews lately. He or she has a lot of 5s and a lot of 1s. 44 ratings in total, so many ratings. And this is a doctor that has gotten better over the years. So the half-life is forgiving the doctor for all the 1s in the past, and now pulling up towards the more recent 5s here. Lastly, look at the 17th doctor at the very end. This person has not been rated once. The old ranking would place him or her last. We say, no, with no ratings, we believe you're in the middle of the pack, so we're going to place you there. Certainly, we think this doctor is better than the person with just a lot of 1s down here. I think that's better. Let's summarize. Only simple problems have closed form solutions, so don't worry so much about how to solve things when you start modeling. Look at what properties you want to model instead. Solving is left to an optimization algorithm. That being said, there is a good reason why people like squared errors. They have some really nice mathematical properties, and not everything that I showed you today can be solved efficiently for bigger models. That's good to know. In machine learning, the solution depends on both the model and the loss function. A lot of data scientists focus a lot on the model itself. They will discuss which model is better in detail. However, the model is important, but if you choose the wrong loss, that's not good either. So for instance, if errors really are relative in your application or multiplicative, 1 order of magnitude worse is as bad as 1 more order of magnitude higher, and or you choose RMSE and you have an economic application, then you're probably modeling the whole thing wrong, and it doesn't matter that much what type of model you use. So I think you should definitely focus on the model, but you should also focus on the loss function and think about that. You should adapt your approach to the problem. You should combine existing ideas, but don't reinvent. There are many good books, there are many good sources, people have thought about a lot of amazing things. So read up on that and don't be afraid to combine good ideas from papers and books. But if you find yourself inventing something that you believe is totally new to solve some problem that you meet in practical domains, you're probably reinventing something, because almost everything has been done. So it probably means you should do a literature search. Sometimes you can have to invent new stuff, but usually you don't. So be aware of that. Always start simple. Never use models you don't understand. You're going to have a hard time explaining them to others, and they might behave in ways that you don't fully understand. It will probably come back to bite you. And I still think there's a lot of room to have fun with simple models and use simple models. So even today, some of these e-commerce sites are literally billion-dollar businesses, and they don't implement averages correctly. So there's a lot of interesting work to be done, even if you don't do the super fancy stuff in machine learning. And it's fun to think about simple things. I hope I convinced you of that in this presentation, because that was the idea, to just start with some simple averages and have some fun and play with it. Now, the final comment that I want to make is that if you go back to the first slide when we assumed that our model was the one parameter model, and you remove that restriction and you have an arbitrary model, everything that I talked about in the presentation still holds. Everything with the loss functions and ways of modeling things still holds. But by choosing one parameter models, I was able to create some nice plots and talk about things in a simple way. But a lot of these things are still as relevant for other models, even though computationally it's not always that easy to optimize. I really hope you enjoyed my presentation. Thanks a lot for watching, and again, you can download the slides and look at the references if you want to. Thank you so much.